Let us discuss some numericals based on design of Butterworth filter. Here we are concentrating on analog type of filters. So we'll be adopting the procedure for analog filter design. The problem statement here is a Butterworth low-pass filter has to be designed for the given specification. The specifications are as follows. The first specification is the passband gain Kp is said to be equal to -1 dB at the passband edge frequency omega p equals 4 radians per second. Stopband attenuation should be greater than or equal to 20 dB at the frequency omega s equals 8 radians per second. We have to determine the transfer function HA of S of the lowest order Butterworth filter to meet the above specifications. Now, from the given problem, we can sketch the desired response. The desired frequency response will look something like this. The frequency response 20 log of HA of j omega is plotted versus omega. Here we can identify the Kp value in the given problem being -1 dB and Ks equals to -20 dB. Omega p value and omega s respectively are shown as 4 and 8 radians per second respectively. Now, if we want to proceed for design, we have to design the Butterworth prototype first. See, prototype filters 1 whose edge frequency omega p should be 1. Suppose we desire to do the transformation here. The transforming equation, the backward design equation here is omega s dash equals omega s by omega p. This would yield the value of omega s dash to be equal to 2, and we will get the edge frequencies as 1 and 2 respectively. Yes, we could adopt this particular method and carry out the design. Alternatively, here in this problem, we observe that we are retaining the same value of omega p and omega s, and let us check out the design here. First, we determine the order of the filter for Butterworth. The order for normalized is given as n is equal to log of 10 to the power of minus kp by 10 minus 1 divided by 10 to the power of minus ks by 10 minus 1 whole divided by 2 times of log omega p by omega s. Substituting the respective value of kp, ks, omega p and omega s. Kp value we know is negative and negative makes it positive, and then we have to divide by 10 or multiply by 0.1. So simplification gives you the value which is 4.2893. The order is never a fractional value. Order always has to be a whole number. So the next step is rounding it off to the next largest integer. Therefore, an order of 5 will satisfy the requirement which is set out in the problem. This is the minimum value of order for which we are supposed to carry out the design. Any order more than 5 will definitely satisfy the requirement. In fact, it may perform better, but the cost and the complexity aspect also increases. Therefore, let us carry out the design for the minimum order n is equal to 5. The first step towards achieving the transfer function of the filter is to locate the poles. To find the location of the poles for the case of Butterworth, we know that the poles are located on the unit circle given by sk is equal to 1 with an angle equals to theta k. The k values to be determined are 0, 1 up to 2n minus 1. Totally we have 2n poles. N will be on the left half and n will be on the right half. For the sake of stability, we have to favor the LHPs. Left-hand poles are said to be stable. Therefore, for order 5, we will determine the first 5 poles as S0 S1, S2, S3, S4. The poles are given by 1 with the magnitude of 6 pi by 10 on substituting in the above equation, considering the value k is equal to 0. Later, this value is converted from polar form to rectangular. Similar way, we can determine the value of S1. We observe that the separation between the two frequencies is given by pi by n. So in this case, it is pi by 5. So if we add a value pi by 5 and simplify, we should get the next frequency. Similarly here, if you add pi by 5 to this number, you should get the next frequency and so on. So this way, we have computed the value from S0 up to the value which is S4. So S0 to S4 has been calculated, and similarly, the values are converted to the rectangular form. Now, if we are aware, we know that the poles lying on the complex plane, they exhibit some sort of symmetry. In fact, we observe that S0 has conjugate symmetry with the pole called as S4. Therefore, it is sufficient that we calculate S0, S1, S2, and the remaining two can be determined on the basis of conjugate symmetry. So, exploiting this particular aspect, we have found the first 5 poles. On the complex plane, we have drawn the poles location S0, S1, S2, S3, S4. As previously mentioned, S0 has conjugate symmetry with S4, S1 has conjugate symmetry with S3, S2 is a real pole because it lies on the real axis. So on the left it is situated at -1, on the right S7 is located at +1. On similar lines, we can actually calculate the values for the remaining poles also, but this will not feature in the calculation. So we continue the process as described, and you can also use the concept of symmetry here also. So S0 will have some relation with S9. You observe that the magnitudes are same, but we have to change the sign in accordance with which quadrant does it lie. So hence we can determine all the 10 poles. Next step is determination of the transfer function. Now we know the general format of the transfer function for order n is given as hn of phi is equal to 1 by pi of s minus sk, and here we are supposed to consider the LHPs only. Now for n is equal to 5, we have the first 5 poles, that is S0, S1, S2, S3 and S4 in rectangular form. Now we already have tabulated the values. In advance, if we are able to arrange it in a particular fashion, it will help towards the simplification process. We are writing the poles which are conjugate of each other beside each other. So we observe that S0 and S4 are conjugate and S1 and S3 are conjugate of each other. S2 is the only real pole which can be written aside separately. Therefore, the substitution of these values will yield the results as shown. In the next step, we are performing the simplification by using the reducing equation a plus b into a minus b, which equals a square minus b square. The simplification step will give you the answer, which is as shown here, 1 divided by s square plus 1 multiplied by s plus 0.309 the whole square, which corresponds to a square, and b square is nothing but 0.951 the whole square. And similarly, we get for the next pair of poles also we get the answer. And finally, if we open the bracket and expand it, the equations will simplify further, and finally the equation will yield finally the equation will appear in the polynomial form. the equation after simplification by opening the brackets and solving for all the terms yields a result which is as shown. So the above equation is called as a factored form of the result, and the below one is called as a polynomial form. So we have got the answer for the normalized fifth order Butterworth prototype. Next we have to design for the given specification. In order to do that, we have to perform the step called as frequency transformation. Now the transforming step involves an equation S being replaced by S divided by omega C. In order to find the cutoff frequency, on the basis of the question says that you have to match the -1 dB requirement exactly and do better than the stop band. Hence, the cutoff frequency calculation is based on the passband edge frequency. We have already seen this equation. Omega C is equal to omega P by 10 to the power of minus Kp by 10 minus 1 whole to the power of 1 by 2n. Substituting the value of omega P and Kp gives you the frequency 4.5787 in terms of radians per second. Finally, the specified low pass filter is obtained by applying low pass to low pass transformation on the normalized low pass filter. This transforming equation is given as replacement of S in the transfer function by S divided by omega C being 4.5787. Therefore, wherever you find S, we change it to S divided by this particular quantity. And after simplification, we get the final transfer function HA of S to be 2012.4 divided by the polynomial which is of order 5. So this is the manner how we can proceed and solve the problem in the case of an analog filter design. If desired, we can check whether the design that we have done is correct. The verification steps are described as below. First thing is, from the transfer function, we have to get the frequency response. This can be done by letting the value of S to be equal to j omega. So wherever you have S, we're going to substitute the value as j omega. After the substitution of j omega, the next step would be to find the magnitude of that value. So we have to perform the steps, which is simplification. We have to simplify it because j square gives you an answer which is -1, j cube gives you a value which is j, correspondingly applying all the simplification steps, and we can solve the equation. So after you do the simplification, the result of the simplification can be shown as below. So this is the result of simplification, where we have isolated the real terms which do not have j and the imaginary terms which involve j. To find the magnitude of a complex number, we can use the formula that is square root of a square plus b square. Hence, a square is the quantity which you have here is a, so square of it, and the quantity you have here is b, so square of that value. Next, once you have the magnitude, we can change it to dBs by taking 20 log on both sides and applying the value of the respective edge frequency. The problem specification says omega p value is 4 radians per second. When you substitute this number, you get a value of approximately -1 dB, which is exactly the specification given. So we are meeting the passband requirement exactly. To test for omega is equal to 8, once again you insert the value 8 in the equation, solve, and then take 20 log of the answer. The result turns out to be -24 dB. The specification set a value of -20 dB. We are exceeding that requirement. We are doing it better. We are getting a value which is -24. So this verifies that whatever design method has been adopted is successful. The next numerical is on transforming the various frequencies. So in the problem, they have given you a transfer function h of s is equal to 1 divided by s square plus s plus 1. This represents the transfer function of a low pass. It's not Butterworth, because for a second order Butterworth, the equation could have been 1 by s square plus root 2s plus 1. So it's not matching. It is clearly mentioned it is HFS. It may not be Butterworth. Now this has a passband of 1 radian per second. The width of the passband is said to be 1 radians per second for this low pass filter, or omega p value is equal to 1 radian per second. Now using frequency transformations, we have to find the transfer function of the following type of analog filters. First one is a low pass filter whose passband is 10 radians per second. The original design has 1, we have to transform it to 10. Next, we have to design a high pass filter with a cutoff frequency of 1 radians per second. Next, change it to a high pass filter with a cutoff frequency of 10 radians per second. A band pass filter with a passband equals to 10 radians per second and a center frequency of 100 radians per second. A band stop filter with a stop band of 2 radians per second and a center frequency of 10 radians per second. So let us start with the very first part A of the problem. So we have to convert it to a low pass filter with a pass band of 10 radians per second. So given transfer function HFS is equal to 1 by s square plus s plus 1, the low pass to low pass transformation is given by replacement of s with s divided by omega u. Hence, the required low pass filter is given as HA of s equals h of s with the replacement s changed to s by 10. Therefore, substituting wherever we have s, replace it by s by 10 and simplify gives you an answer 100 by s square plus 10s plus 100. In part B of the problem is to convert from low pass to high pass, and the value of frequency to be changed is equal to 1. Therefore, we can go with the transformation s being replaced by omega u by s. That is, since the value of frequency is 1, it becomes s replaced by 1 by s. So substituting for the value of 1 by s and simplifying, we can obtain the equation as s square by s square plus s plus 1. Moving on to the third part of the problem. Here we are substituting for s to be 10 by s because this is also a low pass to high pass transformation, except that the cutoff frequency is equal to 10 radians per second. So similarly, substituting for 10 by s in the original equation and simplifying, we get the answer as s square by s square plus 10s plus 100. Part D of the problem is a low pass to band pass transformation. We are aware of the transforming equation as s being replaced by s square plus omega u times omega l divided by s into omega u minus omega l, which could also be represented alternatively as s square plus omega naught square, where omega naught is called as the center frequency given by square root of omega u times omega l. And for the band pass filter, we can have a bandwidth denoted as B naught or simply W or BW, whatever you call it. So it's a difference between the upper cutoff frequency for the pass band, the upper frequency for the pass band minus the lower frequency. So it is omega u minus omega l, which is the width of the pass band. So the pass band's bandwidth or width of the pass band is indicated as B naught here. So we have to substitute the corresponding values given in the problem. So the values provided in the problem is that center frequency is said to be equal to 100. So we have to take 100 square, and the bandwidth is said to be 10 radians per second. So substitute for that bandwidth. So after substitution and appropriate simplification, you will end up with the answer. Next, the last part of the problem happens to be a low pass to band stop transformation. We remember that the transforming equation is quite similar to that of low pass to band pass, except that the numerator and denominator, they seem to be interchanged. So the expression is of the form s into B naught, where B naught is the bandwidth, divided by s square plus omega naught square. Omega naught is the center frequency. From the given numbers, we have to do the substitution bandwidth is set to be 2, center frequency is 10, substitute and simplify, and we get the appropriate result. Thank you all.